Hello and welcome to this video. In this video we're going to look at how would we be able to determine the value for Young modulus of a wire. Now in order to do this we first need to remind ourselves of what is the Young modulus. So the Young modulus is the property of a material that basically defines how strong it is. And we said that Young's modulus is the ratio between stress and strain, but we said that maybe a better equation to be able to express this would be F over A, L over delta L, since this would be the ratio of stress over strain. But what this tells us is that in order to work out a value for Young's modulus, these are the things that we have to measure. Okay, so whenever we start these experiments, we always start with what can we actually measure. And we can measure a force, that's pretty easy to do. We can measure a length, that's again pretty easy to do. We can measure an area, because that's the same as just measuring a length. And we can measure some extension. So all of these things are fairly straightforward to measure, but how do we actually translate from all of this stuff into Y when we have a graph involved? Because basically the idea of all of these experiments is to find a graph where the gradient will give us your answer, because that's the most accurate way of doing any of these things, because it's kind of like taking an average instantaneously. Now in the Young modulus video, I rearranged this equation in the form of F is equal to YA over L times delta L. So that's just bringing the A up, bringing the L down, and bringing the delta L across. Now this is in the form of Y equals mx. Since the cross-sectional area of the wire we're going to assume stays constant. Obviously, this probably isn't going to be the case depending on how much force you're actually applying to the string or the wire. But we're going to assume that there's basically a negligible change in area when we extend the wire. The original length is obviously not going to change because that's the original length of the wire. And the Young's modulus is also a constant, whereas the force that we apply is going to change and the extension we apply is also going to change. Therefore, we know at the end of this, we're looking for an F against delta L graph, and that's going to give us our value for the Young modulus. Okay, alternatively, so this isn't the only way that we could do this. This is probably the most direct way, but we also know that the Young's modulus is just stress over strain, which means if we just make a graph of stress against strain, the gradient of that graph will be Y. So these are two different ways that you could do. Both of them will give you exactly the same answer, because by definition these two things are the same. But let's look at how we're going to actually do it. So our setup for this is we're going to have a clamp stand so that we can attach a piece of wire to the clamp stand on one end of the table, and we're going to try and make that wire run along the table for as long as you possibly can. Now, obviously a table is only so long, and at the end of the table you will clamp a pulley, and the wire will then go down, and we will attach some mass here, and this mass will have a mass M. That's going to provide some force mg, and that's the force that we're measuring in this equation. Now this is going to be the setup that we're going to use. However, before we do this, we need to measure what the cross-sectional area is and what the length of the wire is. So the length of the wire we need to measure with a ruler. So we need to measure the length with a ruler, and make sure that you note down what your error for that measurement is. In order to measure the area of, or the cross-sectional area of a wire, that's pretty difficult to get straight away, but it is possible to measure the diameter of the wire and of the wire. Now the instrument that you want to use in order to measure the diameter of something would be something with a pretty high precision, since if you were doing this with a ruler and you end up with a millimeter, you have your error on that is basically the same as your measurement, which is never good. You always want your errors to be smaller than your measurement, which means we need to then revert to something more like a vernier caliper. But in this case, I'm going to say you want to measure this diameter with a micrometer, since that will give you the most accuracy. And speaking of accuracy, I would say these wires that are usually in a lab, this isn't the first time that they'd be subject to tension like this. They've probably done this experiment with wires multiple times. Or maybe even just in storage, the wires might deform. So what you need to make sure you do is take 3 readings of the diameter along different points of the wire, and then make sure you're basically just checking that the wire is uniform. Check the wire is uniform. Now, ideally, you should end up with the exact same diameter at each point. Then you would only have to calculate one area. If you find that the diameter is different at each point, you would then have to calculate the area of each of those and take an average area for the total wire. If you find that your values vary quite drastically, so a difference of like a few micrometers isn't going to change your result in the end, but if you find that like your thickness changes by something like 0.5 millimeter, that can have quite a big effect on your value. So I would say if you find that your wire has quite a large difference in the diameter across these two, ask your supervisor or your teacher for a different wire, because the wire that you currently have, if it has a very big difference, is probably just on the verge of breaking. That's probably not going to be very safe. Okay, now you can pretty easily go from your diameter to your cross-sectional area, since A is going to be pi d squared over 4. And then all you have to do is plug in your value for d squared and make sure that you're writing down your error for this. And from this point, then you are ready to start taking measurements. However, measuring an extension of this is going to be quite difficult. So what we're going to do is we're going to lay a ruler along the table. And so this here is a ruler. And ideally, we need to mark some sort of initial position along the ruler. And to do that, probably the easiest way is to get just a piece of paper and just fold it so it will make this kind of triangle shape, and it will point to the original value that it was placed at. That obviously means as we add more mass here and this starts to extend, this is going to move this way, and we can measure the difference between the original position and the new position, and that's going to be your extension. And this is a technique that we call the fiduciary mark. Okay, so this is a pretty clever technique in order to basically define your 0 point so that you can recognize if there's any change from that initial 0 point. Okay, now that you've done this, you're then going to begin to add different masses. Since the cross-sectional area we've calculated, the length we now know, we've set up this fiduciary mark so we will be able to measure the extension. We're then going to keep adding masses. In most cases, I would say take at least 6 readings. Definitely take at least 6, but I would say in the case of this young modulus, to try and get a good curve, you probably want to take a lot more readings than that. So I would say take as many readings as you can in the time that you have. So I would say keep adding mass to take as many readings as possible, which would always be the case, but at least 6. And this is basically just going to give you a better curve at the end. So not only will you be able to calculate the young modulus, but you'll also be able to demonstrate the properties of this wire and the fact that it should end up being ductile. Okay, and for each of these, we want to make a table. So I'm just going to scroll down here a little bit. Our table should be consisting of our first column, which is going to be the mass that we've added in kilograms. Then we can convert that into the force in newtons. So to get from this column to this column, we're just going to times by G, or times by 9.81. And then we're also going to need your extension, your delta L, which should be measured in meters, because that is then going to take you the distance from here. That means that we have our values for F and our values for delta L. We want to take as many of these as we possibly can. Also recording errors. And once we have all of those values, we can then calculate a value by plotting a graph. So our graph in this case is going to be force against extension. And what we'll find is, assuming that you're using a wire for this and not another type of material, you will have a graph that will look something like this, similar to the ductile strength that we measured before. Now, what I said before is that delta, or even F, is going to be equal to YA over L delta L, which means the gradient of this line is going to be equal to this factor here. However, the gradient of this line changes as we go across this path, so we just have to take it up to the limit of proportionality. We can't have any gradient past the limit of proportionality, so we're going to take this gradient here, and the gradient here should be equal to YA over L, which therefore means Y must be equal to L times the gradient divided by the cross-sectional area. And this would then give you your value for Y, and then make sure that you're doing your error analysis to get your final value. If instead of doing this kind of expression here, you want to go for a stress over strain graph, the only thing you would have to do is change or extend these this table. So you would have delta L, you could then do F over A to get your stress. Now F over A is going to be in pascals, because that's force per unit area, which is newtons per meter squared, which is pascals. And this would basically be your stress. And then you could do delta L over L with no units, and that's going to be your strain. And then you would plot these two columns against each other. You would end up with a stress against strain graph with the same shape, except you'll have a different gradient here. Your gradient here would be directly equal to Y, and make sure you have your errors. Okay, so from these methods, the setup of it is the same, but your analysis of it is slightly different. But in both cases, you're going to end up with a graph that looks very similar, to be fair. And then you have to take the gradient before the limit of proportionality, and then you will do your analysis on the gradient, including your errors, and get the same value for Young modulus. Okay, thank you for watching.